to start talking about vision and mathematics, and not so much just vision with seeing, but seeing with the mind's eye, because there's an enormous amount of visual imagery in mathematical statements, like equations. Equations are actually descriptions of something that has a visual shape. And we're going to try to explore that. Just as a moment. Jack, are you back there?
Yes.
Can you catch this?
I'm not good at catching stuff.
That ball traveling through the air created a mathematical image. It created a trajectory in the air. You could see it briefly. It was hard for you to perhaps hold on to. It was actually a parabola. It was a parabola in which the height was related to the square of the distance that it's traveling. That's what made the picture. And this is happening all the time, all around us. There is a visual universe, and it might just be the mind's eye, or maybe the mind of the universe, in all of the motions of atoms and molecules and larger bodies like planets and suns doing their thing that makes imagery. So, here's where we're going. We're going to talk about not the whole three-dimensional world. It's too much. We're going to talk about the two-dimensional world, and it's going to be the screen that you're all familiar with, like the screen on your laptop, the screen on your cell phone, the screen on a television set, the screen in a movie theater. That's really the kind of paradigm for this two-dimensional world we're going to look at. And we're going to talk about what exists in that world. It has points, lines, and the full two-dimensional plane, and that's all. It doesn't have cubes and larger structures. And then we're going to talk about circles, hyperboloids, and the fact that these visual images, these things that are pictures, also describe reality in a way that is quite beautiful. We're going to talk about Einsteinian space-time. We're going to learn some Einsteinian space-time in this next series of lectures. It'll be a little bit like learning Cantor's theorem. It wasn't so bad. You just had to know about diagonals. And circles and hyperboloids are going to directly relate to Einstein. So that's where we're going. So let me just remind you about space. If we just have a point, it's the structureless, minimal thing that can exist in space. It doesn't have any dimension. It doesn't have any extent. It's structureless. But it's the building block which you can make other things from. So if I take a point, just look at me for a minute and imagine I have a point here. And this is the plane of the screen. And it's full of a lot of other points. And as I drag this point along, I excite those points and they all turn on. I will make a line. So a point transited through this space, bringing to life all the points that it touches, makes a line. So a line is an infinite number of points. Maybe they're rationals. In fact, if you use a computer, there definitely have to be rationals because we can't make the infinitely long strings of real numbers. And then if I take that line and I sweep it up, I make a two-dimensional space like the screen. And if I then take that screen and I pull it out this way, I make a cube. So from a point, we build lines. From lines, we build the plane. From the plane, we build the cube. And now see if you can wrap your mind around this. Wrap the mind's eye around this. Suppose I take that cube and I pull it out into the fourth dimension. Now, why is that hard for us? Because we live in a three-dimensional world and we involved a visual system that works in the three-dimensional world. It doesn't know how to do 4 dimensions unless you train it. And there are some people who can work at it, can sort of train themselves. And you might also almost be able to see it here. Here is a projection of the next cube up. That's the hypercube. It's in 4 dimensions, and it's being projected onto this plane. This is just a 2-dimensional plane. Your brain is making this look like a 3-dimensional object. And if you just look at this and kind of dwell on it a little bit, can you see a little bit of the cube coming out and it making a bigger structure? It's not essential to do that, but...
How is that not just more cute? It still seems like a 3-dimensional shape, even though it's kind of a bunch of...
It's actually 2-dimensional. It's on the plane here.
Yeah.
There's no third dimension here. But it's pretty easy for us to see the cube as a 3-dimensional object, but it's very hard for us to see the hypercube in 4D. What do you think, Matthew?
That hurts my mind. That hurts my mind to no extent.
Yeah, and I'm going to go back to Adrian's question because I'm stuck in the same place.
Okay.
So to call, I totally see how this one is appears to be 3D. What is it about the next one that appears to be 4 dimensions? What is that extra dimension?
Well, can you follow this? Can you follow this? If I take the plane, take the plane, imagine this is the plane here. Okay? Now it's just a 2-dimensional surface. But can you imagine it sweeping through space here and making a cube?
Sure. Mm-hmm.
That's what's going on.
Right.
What's going on here is the cube is sweeping through 4-dimensional space, and it's making a hypercube. But it's very hard for us to visualize that. So if you can follow this, you're in good shape. That's all we need for what we're going to do. In fact, we don't even need this. We're only going to be working over here for the next 3 lectures. Yes, Jack?
Is 4D like the highest, or is there like, so there's like 5 dimensions,
How many counting numbers are there?
there's an infinite amount,
Yeah, so how many dimensions are there?
and infinite
Yes.
amount?
Yes. But just like we don't work with an infinite number of numbers, we don't work with an infinite number of dimensions. We're always cutting it off. Okay. So our world for this series of lectures is going to be the space of the 2-dimensional plane. That's what we're going to get to try to understand and work with. So I've already told you that that's the artist's canvas, it's the computer screen, etc. Now, the first thing we need to do is know how to address the screen. We know how to pick things out, how to speak to it. So we need a language, and that's going to be this word show. And we're going to show things. What are the things? Well, any point or combination of points and lines, including none or all. And things are addressed by their coordinates. So let's talk about coordinates. So here's our screen. You have one on the paper I handed out. There's your screen. You see the screen. And I have made a pair of coordinates. It's a 2D screen, so we have 2 coordinates. So if you look there, you see the x and I've labeled them x and y. I have to give a name for them. So that every point in here has an address, has a name. And the name will be by giving the value of the x and y that singles out that point. So here we are. Here's you have this you have this in front of you right now. And I have gone ahead and labeled the different lines and points. So you see that the coordinates run from a little over -1. Here's -1/2. This is 0, and 0.5 and 1. And this is the x-coordinate. So all of x coordinates are, and the y coordinates are similarly spanning the same range from a little over -1 to +1. So one point, I didn't label the origin. There's a point that is not, well, there are lots of points that aren't labeled at all. But the first point I want to label is this point. So what's the name of that point? If you wanted to tell the computer, light that point up.
Origin.
You can call it the origin, or in terms of, we have to give two pieces of information here.
0.
Okay. Okay, how many of you have done this before? Several of you. Okay, that's good. All right, so let's run through and see if we can nail down some of the structure of this space. Okay, so one of the things we can do is on the show, which is if we're going to plot things using a computer-aided assistant, the command is usually plot. Plot and show are the same thing. So if we show none, we're not showing anything. And if we show 0, 0, well, there is the origin that you just saw. And the other thing you can say is show everything, show all, in which case all the points are present. You've addressed them all. So let's do 1, 0. Can you plot 1, 0? Now, if some of you haven't plotted before, raise your hand and I'll try to give you a little bit of guidance. And if some of you are pretty good at this and already know what's going on, try to help the person next to you if you can. Marin, are you good on this?
Yep.
Okay, thank you. Gabby, how about you?
I think I got it.
Okay, all right. Jack, you okay?
Yeah, I think good.
Okay. Okay, Matthew, you good? Adrian?
Yep.
Okay. So there we are. This is the point.
Wait.
Did you plot 0, 1 or 1, 0?
1, 0.
Okay. So this unfortunately was 0, 1. But that's so this, the x coordinate is 0, the y coordinate is 1. Actually, I'm sorry, not using the sequence I just mentioned to you. But let's plot x being -1 and y being 0. Okay.
Keep going higher, right? Put that way.
Okay. Got it? -1, 0. And now, how about 0, -1? And we've covered then all four of the, we've gone around, covered all 4 of the quadrants. Okay, so any point you want, just put the coordinates in and the point lights up. But you might now want to do lines. So how do we call out a line? How do we address a line? Well, the convention is to use this same convention. For example, if I wanted to address the x-axis, I would write x0. What that means is these are all the points whose y-coordinate is 0, and its x-coordinate can be anything. So you want to try to draw that line in? It's actually already there, but you can point out which one it is. The y-coordinate is 0, and all the x's can be whatever they want. So that's the x-coordinate itself. All right, let's try now the other case, which is show 0, y. That's the x is 0 and the y can be anything it wants. And there's that one. Okay. Suppose I wanted to call out, I wanted to address this 45-degree line. Do you have any ideas about that? I would like, that's fine for this line, we did that. But how about a 45-degree line? What's true about the 45-degree line, about its x and y coordinates? See, if you imagine, here's the 45-degree line here going up here, cutting across here. For example, here I am at 0.5 on x. Can everybody see me? And here I am, what's the value of y? When I'm up here, what's the value of x? What's the value of y? So what's characteristic about this upward slanting line? It has, the address would be,
Positive number and positive number. Both numbers is positive.
they're both positive, they're even more than that. Can't hear you. Go ahead, say it.
It's identical.
Identical, right. So if you wanted to call out, you could write it this way. If you wanted to call out the 45-degree line we're just talking about, you would write XX, or you could write YY. But that says they're both the same. Or we could write x minus y equals 0. That's the equation of that 45-degree line. Everybody okay with that? So so now we can have a line that's not just one of the axes. It's got a little more interesting structure. How about the 45-degree line slanting in the other direction? Slanting away, this line. How might we do that? Well, let's see, I don't want to get too much here. So that one would be or let's see, is that confusing you? The fact that I'm throwing an x over here? It could also be just the same as y minus y. But this is maybe what you really want to take home. This is x plus y equals 0 and x minus y equals 0. So this is the x minus y equals 0, and here's the x plus y equals 0. So now we can draw slanting lines. And we could draw more slanting lines by putting numbers in front of the x and the y, like 2x plus y equals 0. That will give you a line that's slanting, that's slightly shallower. But if you notice something, first of all, you notice there's no powers here. We're not seeing anything like x squared or x to the n or y squared. It's all to the first power, and they're all lines. So what I want to introduce now is the circle. And I think there's just a little too much here. So I want to take that away. So here's a circle. And the circle has an identification, just like we said x plus y is that right slanting, right and left slanting lines, x plus y, x equals 0, x minus y equals 0. What is the statement that the circle has what is its name that we can call it by? Well, it has an equation. And it's one of the most simplest equations in mathematics. It's x squared plus y squared equals 1. And you notice that it's hugely symmetric, just like the circle is completely symmetric. If I rotate the circle around about its center, well, if it was drawn well, you wouldn't see any change. So it has these wonderful symmetry properties. One is that if you replace x by y and y by x, the equation is exactly the same. It doesn't change. The highest power that appears is 2. There's no cubes or fourth powers. And this is a really important idea. Once we have made a line or a circle, both the line and the circle are one-dimensional objects. They're sitting in a two-dimensional space, but they don't take up the whole space. That's because they are one-dimensional. So it only takes one piece of information to pick a point. To pick a point on the circle. Just one piece of information. That's all you need. You don't need two. You don't have to give both the x and the y. And you can see why it's so, because if I give an x, you could calculate the y from the definition of the circle. It's you just solve for y in terms of x. So the circle is a one-dimensional object, even though it's curved and it's sitting in a two-dimensional plane. So I have to talk a little bit about the circle before we can get on to using it. And one of the fundamental ideas with the circle is the concept of angle. What does anybody want to offer? What is an angle? What is an angle about? You look dubious, Adrian. What do you think, Stella? Have you ever seen angles before? If somebody says, go at 45 degrees, would you know what that would mean? Yeah. And about how much is a 45-degree angle? Could you hold it up, hold your hands up and make it? Pretty good, yeah. How about 90 degrees? That's the right angle, 90 degrees. Excellent, okay. So we're going to have a more rigorous definition of angle because you've seen degrees, 45 degrees, but that's not the most fundamental unit for angles, although we use it all the time.
I want to slow down just a minute because you made a couple of points that are really important. I haven't noticed people taking notes on it. Some people I have, but not everyone. So first of all, you gave that it's a very simple equation of a circle, x squared plus y squared equals 1. If you haven't already written that down in your notes, please do. And then what you're about to say about the angles, I think they need to make sure they write it down.
So the first thing you need to know about angle is it's a distance. It's a distance along the circumference. So angle is like 1 foot, 2 foot, 3 feet, 4 feet, 5 feet, 6 feet, 7 feet, 8 feet. It's telling you how far to go along the circumference. But it's for a unit circle. That's where the radius is 1. So you can't just have any old number of feet in angle. Or if you measure it in feet, you then have to divide it by the radius, so that divides out the feet because the radius is a certain number of feet, and you end up with a pure number. So angle is a pure number. It's the distance along the circumference between 2 points on the unit circle. Unit circle means circle with radius 1. So it's like all the circles have been collapsed into radius 1. So that's what the angle is. And let's take a look at, I think you've probably seen pictures like this before. So if we have 2 points and they're sitting on the circle, they define a certain distance that you have to travel along that circumference to get from one to the other. Forever, mathematicians have called angles very commonly and frequently with the Greek letter theta. My son would get really angry with me for doing that because he hates Greek symbols in mathematics. But he's not here, I'm doing it. This is the traditional symbol for angle. Not always, it could be x or y or some other symbol. So here's the unit radius, that's the 1, and theta, that's the distance. And the circumference, when you go all the way around, I think you all remember this, the circumference is 2 pi r, where r is the radius. The radius is 1, so it's just 2 pi. So this is very important. If you want to write this down and say, remember this. The angle for a complete revolution is 2 pi. That's what it takes to go all the way around. And if you go further than that, you're just repeating yourself. And now we're going to learn about a superpower in mathematics. What you saw when we just plotted those points is that you could plot points that took you around the circle. And I want to show you something that is going to have some really quite interesting properties. Let's see, I don't want you to have too many things to think about here. So let's not just do that just yet. What I want you to think about is I've identified these 2 dimensions by giving them names, the x direction and the y direction. That's fine. But I'm now going to do something a little different. I'm going to say this direction never has anything special marking it out. If there's nothing marking it specially, that's going to be the x direction. But this direction, I'm going to give it a name. I'm going to call it the I direction. Now, right now, you probably are thinking, oh, that's the square root of -1. And indeed it is. But we're just naming that direction right now. So that if I wanted to pick a point, I could say, for example, this point up here, x is 0 and y is 1. So it would be 0 I times 1. But I times 1 is I. All the numbers on this axis are the same as the numbers on this axis. They have the same size, the same distribution. They're all real numbers. The only thing that's distinguishing them is which axis you're on. It says I'm on this one or that one. If there's no special symbol, it's just 1, then that's that. Then it's just got 1. So that the distinguishing symbols are 1 and I. 1 is giving the x-axis. I is telling you it's the y-axis. So let's see how this would work. So there's the I-coordinate direction and the x-coordinate direction. Now let's look at what happens here. So suppose you didn't know anything except this rule I'm going to give you. I to the 1 is just I. That's standard algebra. But I'm saying I squared, which is I times I. I'm going to say that's going to be -1. Don't worry about square roots. Don't think about it right now. That's the rule. When you square I, it becomes minus 1. But look at what happens now. Suppose we want to cube y. We want to multiply it by another I. So that's an I squared times an I. Well, I squared is minus 1. There's the minus 1. Here's the other I. Minus 1 times I is just minus I. So we see that this amazing superpower is that the cube is minus I, the square is minus 1, and the first power is I itself. Let's go one more. Let's multiply it by another I squared now, I to the fourth is I squared times I squared. I squared is minus 1. I squared times I squared is minus 1 times minus 1. That's plus 1. And lastly, let's do it one more time. Let's hit it again. Another I. That's I to the fifth. That's I times I to the fourth. But I to the fourth is 1. So this is just I. And what happened? We went back to here. So by raising I to these powers, we go from I to minus 1 to minus I to 1. Let's see if I show you what this looks like. So let's start out. So here's I. When we multiplied by another I, we got minus 1. So we had I squared is minus 1. So that took us, if you can keep this in your mind, when we started with I, we're on the vertical coordinate, on the I coordinate. When we squared it, we went over and we got to minus 1 on the x coordinate. When we cubed it, we got to minus I. That's minus 1 down here. And when we raised it to the fourth power, we came back to 1 on the x coordinate. What's happening is we have this sequence that goes I minus 1 minus I 1. I minus 1 minus I 1. It just keeps repeating. And what's happening, you can see that if you start here with I, you multiply, you hit it with the super operator I, it rotates it by 90 degrees. Because now you're at minus 1. Let's try that again. I'm here at I, that's this point up here. It's I, 1 I. I'm on the I-axis with the value 1. I multiply it by I. It becomes I squared, which is minus 1. It rotates to here. Let's do it again. We multiply the minus 1 by I, and it becomes minus I, so it rotates to here. Do it again, and it becomes 1, and we've rotated to here. So I, this super operator I, is a 90-degree rotation. What do you think, Stella? Okay. Jack, what do you think? Is that kind of coming clear, or does it seem you want me to say a little more about it?
It actually makes a little bit of sense, actually. Although all I knew was that I never knew that there was an I coordinate or thing.
Well, it's a name. We have 2 coordinates, so I have to be able to call them. I could have called it the Jack coordinate. And I said you take Jack and you multiply by Jack, where Jack squared is minus 1. Jack times Jack is minus 1. Jack cubed is minus I. Or no,
Minus Jack.
minus Jack. Got it?
Yeah.
Okay. What do you think, Andrew? I think, Adrian? Okay?
Yeah.
Okay, Matthew? All right, so let's go back to this. So you say, well, that's fine. I can rotate by 90 degrees. But there's a whole lot of other points on this circle. How do I get to them? Here's what's really magical. If you raise I to the m power, it rotates the point by m pi over 2. Now, you don't have quite yet the preparation to prove that, and I don't expect you to. But we can get to all of the points in between by multiplying by m. And m can be a number, a real number. It doesn't have to be an integer. Okay. Now, I felt that that was enough new material for today. So we could, I could answer some questions about it. Well, maybe I'll just say one more thing, which is running ahead, but that's okay. So we saw, without ever mentioning the square root of -1, we just made a rule that we have this operator I, and it's equal to, when you square it, it's -1. I think I keep losing the pins, but that's all right. I think it'll.
You need a darker one?
I think it's just the board.
Oh, the green one works.
Okay, thank you. It's pretty light, isn't it? Oh, it's not bad. Very good, thank you. Okay, so we said that there's this operator I squared and it's -1. And then we said that I raised to the m.
This is a dark one.
Oh, thank you.
It's fresh.
So the angle that you will rotate to is m times pi over 2. And m can be any number. Now, what I'm going to leave you with, and we'll try to work on this next time, is that this amazing result, this amazing thing, that e to the I pi over 2. What does it mean to raise e to this power? Well, you just saw we're multiplying the I operator, and we were able to rotate around the circle. And if we put the m in here, that's I to the m. This is one of the most amazing things in mathematics. It's all over the place. It is fundamental to so much. And it's this fundamental relationship that has to do with this, what's called the complex plane. You can't do this in 3 dimensions or 4 dimensions or 5 dimensions. There's only this superpower magic that comes with 2 dimensions, and it's because of the very nature of the way numbers are put together with complex and reals. And yes, you can now bring in the square root of -1, but more deeply, it's really about working in 2 dimensions. that complex numbers show that that the number system is a two-dimensional number system, essentially. It's not just one dimension. Now, you can stay on the real axis all the time and always just strictly work with real numbers. Okay, should I just do this all again? One more time?
I think we got it. What do you guys think?
All right, well, I am now going to, any questions on this, about this new super operator? I didn't realize it would go quite so fast. And I don't have a whole lot more to say about it because I don't want to get into this just yet. We'll save that for next time. All right, well, one of the things I wanted to do today was just set more firmly the last bit of the infinities. And I want to start by reminding you that we did show that if you have an infinite string of countable numbers, which are the integers are countable, and you put a bunch of them together and make them infinite, you have an infinite set, that this is countable, and we did it with what was called the cobweb proof. I think you all followed that. Now, what I want to kind of emphasize here is this is not the string of integers. We have an infinite string of bits. It's not the infinite string of integers. If it were the integers, we could count them using the cobweb proof. I didn't make that clear enough last time. So this is not the string of integers. It's an infinite string. And what we want to do, we would like to prove that it might be countable. In fact, people did try to prove that it was countable, but they weren't successful. So what we must do is allow that a countably infinite set of these infinite strings may or may not be countable. We don't know ahead of time. And that's why we can't say that this is countable by the cobweb proof. It may not be. In fact, what Cantor's proof shows is it's not. I didn't make that as clear as I would have liked it to be. So Cantor showed that we will fail to do so with that diagonal argument. And as you recall, that had to do with listing all the strings and showing that you could make a new string that was not in the set, and therefore the set couldn't be countable. And it happened by reversing the bit on all the diagonal entries, so that the first string is not in the set. See, it starts with a 0 instead of a 1. The second string starts with a 1 instead of a 0. The third string has on the diagonal the opposite bit, and so on. So this string is new, and it's not in the set. And this diagonal argument was one of the really beautiful arguments in all of mathematics, and it's used in other areas that are very similar to this in number theory and in computer science. So I wanted to go over that and emphasize that from last time. And so here's one last look at the world of infinity, which we're now going to pass by. Infinity plus 1 is infinity, infinity plus infinity is infinity, a half infinity, infinity times infinity, everything is infinity, no. 2 to the infinity, which is this infinite number of infinite strings, is bigger.
Would you use infinity like a variable? Would you?
No.
You wouldn't say like infinity times infinity?
No, I tried to emphasize that by saying infinity is more of a concept than a number, but there are numbers that label sets, like the set of all of the uncountable numbers so that you could give a name to that set, like it's an uncountable infinity. So the sets of infinity that are beyond countable infinity, and mathematicians are very inventive. They've got hyperreals, it goes on and on and on. But if you're thinking about and kind of getting your feet on the ground here, don't try to use infinity like a variable. Well, I think that's pretty much what I had to say today. Do you want to ask me any question on anything? How about the homework? I don't know if most of you got it, but I sent out the answers to all the homework this morning.
Did any of you get that?
Yes.
So where are you at with what has been presented today? What stands out for you? Or what are you making of what you've experienced? I mean, your mind does something with it, whether it goes into a daydream or goes into a connection to something, some other thing that you've been doing in math with Ezekiel.
The concept of a hypercube is like crazy. It is really crazy because we're in a three-dimensional world. Our minds can't even imagine it. It's really cool.
You can mathematically describe it. Here, now this is a good, thank you, Matthew. There's something I can say here that I think will be really helpful.
Again, the black one I just gave you is brand new.
Oh, okay, well, I'm going back to green. I like the green. Okay. X squared plus y squared equals 1. That's the equation of a circle. And it's in 2 dimensions with x and y. What do you think this is? This is a circle. What do you think that shape will make? First of all, it's going to be embedded in a 3-dimensional space because we have 3 coordinates, x, y, and z. So I think you've probably seen.
Yeah, especially those of you who are learning to use the 3D modeling software, whether you did it in SketchUp in Green Building or those of you who are now in Fusion 360, we're working with these 3-dimensional planes to start off designing the car body.
So what this is a circle is a one sphere. It's a fancy name for a circle, but it's got to do with the fact that with x squared plus y squared equals 1, there's only one free coordinate, which is the angle. So the circle is called a one sphere, and it's a sphere because it has this beautiful symmetry. And this is a 2 sphere. The 2 sphere, and what that means, it's the basketball. It's not the inside of the basketball. It's just the surface. And it takes 2 coordinates to tell where you are on that surface. Incidentally, you might like to know that the name of the solid, which is a 3-dimensional object, is called a ball. So the ball is the big solid, but the sphere is just the skin. Just the skin of the ball. And so, I don't know if I can draw one here. But So that's points that lie on this sphere, x squared plus y squared plus z squared equals 1. Now, Matthew, this is in three-dimensional space, so you're happy with that, I think. You can visualize a basketball, right? Okay. You can see you can keep playing this game. So the equation x squared plus y squared plus z squared plus w squared equals 1 is a three-sphere. And do you think three spheres exist? Actually, the motion of a planet around the sun lies on a three-sphere. Not the physical space is only one part of it. The other part of that space is its motion space, where its velocities are. And those things lie on a three-sphere. So they're real. I don't know. We're not going to do that in this course. We're going to just work on the many features of the plane and the circle. But we're going to bring in another shape next time, which is what happens when we blow the circle apart. So I'm going to erase all this higher dimensional stuff. Don't want to make Matthew upset or anybody else. Back to just where we were on the circle. Was there a question?
I was just saying, when you said blow the circle up, that sounds interesting.
It's very interesting because that's where you get Einsteinian space-time. So, well, I'll just leave it for one. If you just change the sign, one measly little sign, in that x squared plus y squared equals 1, you make it x squared minus y squared. It blows the circle apart. I don't know how long I can continue with this preview, but yeah, you can let people out early. Yeah. Alex, I think, needs a little more sleep. No, you're okay?
Where are you guys' brain level at in terms of, is your brain full? Do you have room for more? Are you ready to take what you've got? This is your choice point. If you speak up, you can get what you need and what you want. Do you want to go farther? Do you want to take a break?
My brain is still pretty full from last lecture.
Yeah. Right. Okay. So why don't we call it today, and why don't you share the, I wrote some comments and discussion about the problems, and I do have to say that many of you did not submit any problems at all.
I did just a few minutes ago.
Oh, okay.
I realized that I had typed the entire email up
Oh.
and then gone to another
Okay,
page.
well,
and that's just it.
I'm not any kind of policeman here. I would suggest a little extra time that we're giving up here today, you try to invest that in just looking at the last problem set, looking at my sketch and comments about the solutions, and also do that. Share it with them. I don't mind if you work collaboratively on the problems. That's fine. I wanted to also say that in that little list of terms that I sent out for you to just see, what do these mean to you? Bit, string, exponential explosion, and so on. Oh, there are only about, 8 terms, but you could just review them in your mind and see if, yes, I know what that means. And that's a good thing to also do with somebody else if you do it together. Matthew.
If 8 bits are in a byte, how many bits are in a terabyte? It's just, I don't know. I didn't think.
Well, it's a terabyte times 8. Huh? But that's not the number of strings. I think this is still I think this is still something that not all of you are completely settled with. Is the difference between the number of bits, which are the physical things that you're working with, they're like the light switches, the switches, and the number of strings, which are the informational, which is the amount of information you can put in those switches. And the amount of the number of strings is an exponential of the number of bits. That's what we talked about as the exponential explosion. So, if you have byte is 8 bits, you're not asking me about the strings. That's another story. If you ask me, how many strings can you make with a terabyte? That's 2 to the power of a terabyte. Are you good on that?
But not the same.
Oh, it's nothing. It's nothing compared to some of the big numbers that you can imagine. So the number of bits is the little guy. The number of strings is what's really big. From just a few bits, you make exponentially many strings.
So just review what you're asking them to do with the time now is to review the homework. If they haven't submitted it, finish it and submit
Right,
it.
right.
But those of them who have, they can review your answers to the homework or your comments to the homework.
Right.
And then also review the terms and their understanding of the definition of each.
I think that's a really worthwhile exercise to do, is to,
Sound good?
yeah,
All right, and it'd be okay for them to work in pairs for that?
absolutely.
All right, so why don't we break up and we'll just stay down here for this last half hour if you want to get with pairs and do that, and then we'll head up for lunch. And you-
And if you want to ask me any questions about it.
Okay, that would be good. So you
Yeah,
can
all right, well,
around
let's,
between-
why don't you start, let's look at the first problem. The first problem is, who has the problem? I don't have it in front of me, the list of problems.
Want me to pull it up or I can pull it up on that?
Yasha, you had it last time. Do you have it? Thank you.
David, there's your, and it's up here on the screen.
Oh, okay, okay. Did everybody look at the video of Vi Hart? Did some of you have trouble accessing it, or it wasn't performing for you? One person did write that it said that she couldn't look at it. She couldn't look at it. But it looks like most of you were able to look at it. Okay, so that wasn't the only thing I'd asked for you to do was write a short 3-sentence review. What was useful to you in that? What left you confused? And many of you wrote nice short reviews. So let's go on to the next question, which is, this is the license plate question. What I have are the solutions here. Yasha, can you read the question?
The second question is the YouTube question.
The second question is YouTube, right?
I've learned that you need to be like very specific if you're looking for like certain stuff on YouTube.
Mm-hmm.
It has to be very specific. Otherwise they won't understand. You'll get like
Is that on a search? If you're
Yeah.
searching for something with yes. Now in that case, you're not searching for you might be searching for a very specific item, but it's going to find lots of things that might come close to where that is. So you might have to be very specific. But this question was just about, okay, if you're Google and you've got all these YouTube videos, how many bits do you need? How many slots do you need in the name? I mean, do you need 100? And I'm told that YouTube has about 1 billion videos now. Did anybody check on that? I don't know if I'm right about that.
Yeah.
What I could find was it had like slightly over 1 billion.
Okay,
Yeah, I found like 1.2 billion as of December.
okay. So that's a good number. So there's about 1 billion videos. Now you have to put names on all these. Now you could use the numbers from 1 to 1 billion, but you can do better than that, right? Because you know about bits. You know that you can use combinations of bits. So you don't need the numbers from 1 to 1 billion. In fact, what's the relationship? Well, this might be slightly confusing to people because we talked about bits so much. Number of strings to the number of bits. N is the number of bits. But this is a YouTube video, and they're not using just 2 symbols. They're not using a bit. Well, eventually in the computer it'll all be bits, but they're using the upper and lower case of the alphabet, as far as I could tell. Upper and lower case of the alphabet, and the numerals, the 10 numerals, 0 through 9. And that's what they're using. So they have 52 plus 10 numerals. And they use an underscore, but I think the underscore is always kind of showing in the same place in the string. So I think they're using it for a slightly different function. But I said, go ahead and throw that in. So when you add all up together, you get what? 63 symbols, is that right?
Yeah.
Okay, so we have 63. This is for the bits. And I called that, I was trying to get you to think about so the bit is a 2-it, and any other kind of bit, any kind of other kind of set of symbols is however many symbols or options or choices there are it. So there are 63. So the thing that goes here, I'm going to write this now. Number of strings is equal to number of choices raised to the n. And n, again, is the number of bits, the number of its, rather. So there are these things which I'm calling it, when it's not just a bit, but it can have more than two choices. We're calling that an it. And the number of its that each one of these has a certain number of choices. In this case, for this problem, it was 63 for the YouTube videos. And then you take that and you raise it to the power, which is the number of those things that you have, the number of those choosing things, those things that have choices. And I think this is still not completely settled, and it's perfectly understandable. It's a kind of new concept for many of you. So the number of choices is the base for the exponent, and the exponent is the number of those choosable things, those number of choosers, the number of switches, the number of its, and it's also the thing that exponentially explodes when you raise it to the power of the total number of those things you have on hand. So I think in this case, it turned out that it's fairly modest, like 5, 6.
Yeah.
Now, if you look at the typical string for YouTube videos, it's more like 11 or 12. So what that tells you is that they have some other purposes at hand than complete economy. If you wanted to use the minimum number of bits, this is the calculation you would do. But if it's so small that they could organize their information in a slightly different way and waste some of their names, it's worth doing, and they apparently do that. So is the license, any other questions about this? So the key thing to try to get your mind wrapped around is the exponential explosion. Know what goes into getting exploded and knows what goes into where the power is. It's the number of the things that you have, and in the base of the exponent is the number of choices in that thing, the number of different settings of the switch, or in this case, the number of different symbols that you're going to stick in a slot of a YouTube name. Are you going to put the 9 there, or the 1, or the capital A? And how many of those choices are there? Each one of those slots has 63 choices, if we just do it crudely. We don't know about the underscore. They seem to have other purposes for it. Okay. The next question is essentially the same kind of question, with a little bit of just getting familiar with the lay of the land. I asked you to find out where the states with the most cars, state with the least cars, and to find out how many digits they need to put on their license plates. And I think most of you actually got this pretty well. It's the same problem. In this case, the number of choices we said that for a license plate, you're going to use the all uppercase letters. Some states do use a few lowercase letters, and some of them have funny different kinds of arrangements. We just said uppercase and the digits of 1 to 9, so 0 and O, don't get confused. So we only have 25 plus 9, is that right? 34 or 35? So the number of choices is 35. Because we said we're only going to use the capitals, we're only going to use uppercase, and we're going to only use 1 through 9. So the rule is the number of strings is the number of choices raised to the number of things. Well, what are the things in this case? The things are the slots on the license plate. That's what we're looking for. We want to know how many slots have to be reserved. So the number of choices is raised to the number of slots. So that's 35 to the n, where n's the number of slots. And that's supposed to equal how many cars we have. So you stick in the number of cars. I think California has tens of millions, right? I don't know, 30 million, for example. We'll just take that as an example. What you're trying to find is how many slots on that license plate are needed. Jack.
I accidentally misunderstood this question. I didn't know that we were supposed to do like different states. I just figured out the overall total of all cars in America.
That's an interesting number. What did you get?
253 million.
Okay, and how many slots do you need? If all of the license plates are for the whole country, so we don't say California, we just have US. How many slots did you find?
Didn't get to doing that.
Do you remember? Well, it's going to be,
Big number.
it might be 10 or 11, something like that.
Yeah.
Yeah.
That makes sense.
Okay, so the other thing that I want to point out about this problem, and first of all, I want to affirm what some of you did, I think because you're a little uncomfortable with logs. What you did was you say, I want to know how many slots. I know I have 30 million cars, and I know I have 35 choices. I'm looking for the in. But you didn't, the in is actually officially, if you worked it out, it's the log to base 35 of 30, well, all right. Let's just say 1 million. You don't want too many threes floating around. So that's what this number actually is. And if you put that number into your typical mathematical assistant, like Wolfram Alpha, you'll get that number, and it'll be, I think, about 5. Now, I don't know if anybody was tempted, maybe I don't have to worry about that, but would you have taken this to base 10? Did anybody think that maybe that's what you're supposed to do? Well, actually, most of you did not take the logs. What you did was something equally creative. It was a good plan to have. You just tried different in values. You tried n equal 4, 5, 6, saw what the number came out to be for the power, and then you saw that one of them overshot the number of cars and one of them undershot, and so you kind of went right in between. And that's a perfectly okay way. But if you took the log, you would get exactly the number. You wouldn't have to do this hunting and pecking. So I still recommend studying the log on Khan Academy and getting comfortable with taking logs. Let's see, was there anything else I wanted to say about that? Oh, obviously you had to round. If you got 4.6 slots, well, you can't make a 0.6 slot, so you have to round up. And the other thing you might, which is that states want to keep a lot of slack. One of them obviously is for more cars. But obviously there also is the problem of reserving certain symbols. You don't want, apparently, I don't know, I'm not in the license plate business, but apparently you don't want Z, 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 Z. I think it's possible because it's very hard to distinguish it. If you have Z, X, Y, 1, 2, 3, I guess, and you're a state trooper and you're trying to read it, Z, 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 was that 5 Z's, 6 Z's? But Z, X, Y, 1, 2, 3 reads a whole lot easier. I think that's why they avoid it, but I have no idea of why you don't want A. And then, of course, since every combination of symbols appears here, all the profanity and swear words are also going to appear.
Actually, they also do it where, for a while, they'll put, say, if you have 6, they'll do 3 letters, then 3 numbers. So
Right.
you can only have combinations that are ZXY 1, 2, 3 style. So you can't have, say, 1Z, 2X, 3Y. So all of those are.
I think you're right, yeah. Of course, you can have your vanity plate, right?
Yeah.
Jack?
For license plates, you also it's only a certain amount of digits, and you can't really have like your full. You can't do like your full name all the time, or like a full like sentence. You have to like abbreviate.
Well, yes, you have to live with how many digits they'll allow you.
Yeah.
We can get under that number of digits for a band like.
Right, right.
Because I don't know anything about license plates either. Other than they come from different states. Yeah. And that's what makes them fun to count.
Yes, it's like you have another it, which has 50 choices. So when you add the states, you're going to put them all on one license plate. So the state is distinguished by, well, you don't have to distinguish it, you can just count all the cars up. But it's like another piece of information is which state the license plate belongs to, and there are 50 of them, so that that it is a 50 it, if you did it that way.
Yeah. Because I've yet to actually reach like all 50 states. It's usually on the highway that I see more like different little states. Even
Sure.
I think I once saw like Hawaii.
Right. Came over on the boat.
Yeah.
Okay, on the last question, I just want to point out that what I did was point out a fundamental problem in biology. Proteins, did anybody look up proteins in Wikipedia? Were you curious enough? No takers, or you didn't look up proteins or amino acids? Well, for our purposes, just think of a protein as a string. And what goes on the string are these amino acids. Think of them like beads. And they have 20 different kinds of beads. And so the question is, if we have a string of 400 beads, how many exponentially exploded strings do you have if you have 400 its? Same problem again, so that it's going to be number of strings is equal to the number of choices, that's 20 different choices at each bead, and times raised to the power, I said a typical protein has about 400 amino acids. This is an impossibly large number. Yes?
Makes sense that I have a lot of amino acids. As I once just for fun, I was trying to figure out what the world's what like the longest word in dictionary is. It's 45 letters, but then there's this protein that is that would take 3 hours to pronounce, and it's like 187,889, something around there. It's like, geez, that's a big number.
Well, if you have a lot of proteins and they all have to have a name,
Yeah.
you're going to have some names like that.
Start numbering them.
Well, that's not necessarily the best for the human mind. We like to somehow classify things and then subclassify. So first of all, put things into a big bin, and then in this bin you have some littler bins, and in the littler bins you have yet littler bins. We try to use, that's called a tree structure. We try to organize large quantities of stuff by breaking them up into categories. So you might well ask, well, nature could conceivably make a number of strings that's greater than the number of bits in the universe. But nature doesn't. And the basic answer to the question is that when you put these amino acids together, they don't all stick together with the same degree of fastness. Some of them barely stick together, and some of them don't like to stick together. So it's actually a very small subset of the amino acids that will go on your string and stay there. What happens is that the string is made in the cell by a thing called a ribosome. So it's actually chunking out this string that's made from the genetic code. And when the string comes out, it coils all up. It coils all up into this huge, complicated mass. And that's where all of the behavior of that protein is that's regulating all the things in your body. So that complicated structure may chuck out proteins. It may not work with certain amino acids. And apparently it doesn't. But I don't know all the details about this. But that's the basic answer is not all of these things are fit. They're not all fit for life. Are we ready to break? Okay, well, thank you all for coming, and
Thank you so much.
we will continue with the wonders of the circle next time. We'll blow it apart.